NMR means nuclear magnetic resonance. You already got in your AS class that's mass spectroscopy, and also you got IR spectroscopy. NMR spectroscopy is another spectroscopy which is more precise, more accurate than the previous two. These all spectroscopy are used to identify unknown substances. And the spectroscopies are not chemical experiments without using any chemicals. They are device. These are highly sensitive devices, and including computer. They automatically work and give the result, give the output. And in chemistry, we don't study how the spectroscopy work. We just get a slight idea about how they work, not in details, because the machines and the devices use they're multifunctional. There are many things, and we just use their spectra, the outcome that we get in the computer monitor. And as a chemist, if you just can understand the spectra displayed in the monitor, that is enough. And understand means with the spectra you are able to identify the chemical substances, and this works on certain properties of atoms involved in the molecules. Atoms consist of a nucleus, and nucleus consists of protons. Like electrons, protons also spin, and when charged particles spin, then they gain magnetic properties. So what happens, every of the nucleus of the atoms are tiny magnets, and when many magnets are together, then they interact each other in the same domain. They also interact with other atoms, other adjacent atoms or neighboring atoms, because the neighboring atoms also contains protons, also contains magnetic field. So there they interact with each other in multiple ways, and after they interact, still they have each of the atoms has effective magnetic field. When they interact, their magnetic fields are changed, but altogether after interaction, they still have a magnetic effect. Okay, so when you think about a molecule, maybe ethanol thing, look, there are many atoms, and all the atoms do not have the same environment. When you think about this carbon and this carbon, these two carbons do not have the same environment. Why? Because the other adjacent. Yeah, this carbon contains OS, but this carbon doesn't contain OS. What is say? The nucleus interact with the adjacent or neighboring nucleus too, which means the nucleus, the magnetic field of the nucleus is not same. Okay, so this is sometimes, but sometimes they have same environment. I give an example here. Look, CH3, and I write here another CH3. This is ethane, But if you think about this carbon and this carbon, these two carbons have same environment, because this is bonded to this carbon and this is also bonded to 3 hydrogen atoms. And for this carbon you get the same thing, which means these two carbon atoms have same environment. They're adjacent, the neighboring atoms are all same. But that you don't get for this carbon and this carbon. So this is how you may get in a molecule, you may get some atoms having same environment and some atoms having different environment. And if you get this here, the hydrogen atoms in second molecule, the hydrogen atoms here are 3 and here are 3. All 6 hydrogen atoms have same environment, and all 2 carbon atoms have same environment. Why? Because all 3 hydrogen atoms bonded to a single carbon, and so when all 3 together bonded to the same carbon, then the bonded atom, which is mother, you can think the host is carbon. Host is same, so 3 hydrogen atoms would have same environment. And as this CH3 and this CH3 same environment, in the same environment, which means here total 6 hydrogen would have same environment. And if you think the first one, ethanol, here you get CH3, this 3 hydrogen in the same environment, but get here 2 hydrogen, and this wouldn't have same environment with this, because these 2 hydrogen atoms are bonded to this carbon. This carbon contains bonded to an oxygen atom, but this doesn't. So you already got these 2 carbon atoms have in different environment. Here you get these 3 hydrogen atoms in same environment, and there's 2 hydrogen atoms in same environment, but not all 5 in the same environment. And accordingly, you got the OH here, OH, this another hydrogen, that hydrogen would have again different environment, which means you get in ethanol, atoms are in 3 different hydrogen environments. And what I told at the beginning, that each of the atoms have a nucleus and tiny magnet, and the tiny magnet interact with each other, and this interaction depends on their environment. What are the other atoms are around them that they interact with them. So when you get ethane, here you get this carbon and this carbon have same environment around them, so their nucleus, their magnetic field would be same. And so here you get all the atoms are in 2 environment. So this is how we study the environments of the atoms involved in a molecule, and based on the environments, their nucleus, their magnetic field of the nuclei work, and they are also different. The magnetic domain, the magnetic strength are different. And now another thing, so you should consider all the atoms having a tiny magnet in the nucleus. And when a bar magnet is placed on Earth, then the bar magnet align with the Earth magnet. Okay, so same thing happens here in the device. If you place a strong magnet around these molecules, okay, so all the nuclei, all the magnets, tiny magnets, will align with the external magnets. When you put the sample, drops of sample, you put their input as input, and there is already set a strong magnet, and with the strong magnet, all the atoms, all the tiny nucleus with the magnetic field align with the strong device, strong magnet. Okay, using radio wave, the alignment could be changed, as a bar magnet is placed on Earth, on the surface, and this could align with the Earth magnet. And if you want, you can change its direction against the alignment. Okay, and which one is stable, alignment or anti-alignment? Certainly stable is natural alignment, but you forcibly can topple the alignment, and then this would be its position, and this needs energy, no? So that can be done here when all the tiny magnets align with the external magnets. Using radio wave, the alignment can be toppled, changed. But the interesting thing is, all the tiny magnets here are not in the same environment, so their strength are not same, and so they don't need same amount of energy or radio wave. So when they will be changed, their magnetic field will be changed depending on the environment, different environment, they will absorb the energy, radio wave. Okay, so this is the mechanism, this is the main thing based on which this NMR spectra is made. Okay, the device needs some more thing, scale, reference scale. Reference scale means when you measure mass of a substance, suppose versus mass, you use gram. Gram is a reference. Using gram, how many gram here could be 20 gram. So this is 20 times heavier than 1 gram. And if you measure its length, you are using reference. Suppose centimeter is the reference. So for this scale, here you need the reference. So as reference, they use a chemical substance compound, which is TMS. It's called TMS. It's a tetramethylsilane. Silane means here is silicon, and tetra means 4. Here are 4 methyl. You can also write this formula as here CH3 with 4. This TMS is very good choice because and all the hydrogen atoms in the same environment. Another thing I say that the device also needs a solvent. Solvent means the dissolving substances, dissolving solvents and dissolving TMS, etc. And what is that? This is carbon tetrachloride. Carbon tetrachloride is good choice because this doesn't have hydrogen atoms. And the total device is a machine, and machine is very complex, and you can put any of the samples like this, and that would automatically work and would give a displayed spectrum. And you need to understand the spectrum and identify the molecules seeing the spectrum. Another important thing is some NMR device focus on hydrogen atoms. They scale based on so far I was giving you the model or examples including TMS, etc. This type of device based on hydrogen atoms, and some other types of devices also there that works on carbon atoms. The scale or the displayed formula. I mean here the device will mainly monitor how many environment of hydrogen atoms. Here there's 3 hydrogen together in an environment, and this 2 hydrogen in another environment, and this hydrogen in another environment. And you will in the displayed spectrum you will get 3 peaks for 3 environments of hydrogen atoms. And another type of device that also works on carbon atom scale. That's a carbon scale, depend on carbon atom. So that would show there's 2 peak. They're all simple things. After that, we have 2 types of spectrum. One is called low resolution spectrum. Another is called high resolution spectrum. Low resolution spectrum is very easy to understand, and high resolution is more precise and gives information more accurately. We first study low resolution spectrum. In low resolution spectrums, you will get peaks, and the peaks give just 2 types of informations. One, how many environment of hydrogen atoms, and you already got this. This ethane has just 1 environment of hydrogen atoms. So in the low resolution spectrum, you will get 1 peak. And for this, ethanol has 3 different environments of hydrogen atoms. So in the low resolution spectrum, you will get 3 peaks. So this is one piece of information that you get in low resolution spectrum. And you also get another piece of information in low resolution spectrum, which is the area, peak area. You get the peak size will be different. Why? Because here are 3 hydrogen atoms, and here 2 hydrogen atoms, here 1 hydrogen atoms. Based on number of hydrogen atoms in each of the peaks or each of the environment, you will get the peak size. Okay, so this just gives according to the ratio of the numbers. Here you get 3, here you get 2, and here you get 1. Your peak size in the low resolution spectrum will also be at this ratio. This is the scale, and then get 3 environment, so you will get 3 peaks. And I show you 3 peaks. This first peak will be the big one, because here you get CH3. CH3 means 3 hydrogen atoms, and then another is CH2. So according to the ratio you will get a little smaller peak, and here you get one hydrogen atom. So here you get a small peak. So look, this would be double than this, and this would be triple than this. Another peak we also get here, small peak at the rightmost corner. This is for TMS. This is the scale, and the ratio doesn't mean the exact number. Here you get CH3 3, 2, 1. This gives just ratio. So thank you very much. Now I'm giving you a few more examples of low resolution spectrum of NMR. CH3O is methanol. If you analyze this compound in the NMR spectra, then you will get the spectra just with 2 environments. Here you get 3 hydrogen atoms bonded to this carbon, and so all three will be in the same environment. Here is another hydrogen atom that is bonded to oxygen, so it's clearly their hosts are different and different elements, so would have different environment. Peak ratio would be, one would be 3 times bigger than the other. This is 1/3 of this, okay? And here will be a small peak for TMS, and this is in propanol. There's two, and these two hydrogen atoms are in different environment. Why? Look, if you get this group is attached to OH, and this group is not attached to OH. So this two, altogether 4 hydrogen atoms, not in the same environment. Then how many peaks should you get here? Accordingly, you get 4 peaks. In the first peak, you get 3 atoms, so this will be a bit bigger. And here you get these 2 peaks for this CH2 and this CH2. And they will be smaller, and this 2 is smaller will be equal in size. Look, equal in size according to the ratio. And the last one you get this small one. Last one that is a small one. But if I give another example here, look carefully. I'm giving here another OH. Then can you estimate how many environment would be here? Yeah, here are 2 environment of hydrogen atom. This is very important, you must know. Look carefully. This 2 hydrogen atoms and these 2 hydrogen atoms are having now same environment. Why? Look, what is on left side, what is on right side. And that you get for these hydrogen atoms. On both sides you get the same thing that you get here. Okay, just you be there and look this side and this side. And you just be there and look this side and this side. You would give the same thing. Now think that peak size. Here are 4 hydrogen atoms. Here 4. Together is 4 and it is 2. So what you get 4:2. That means 2:1 or 1:2. So one would be double and another would be just half of that. And is a TMS. So this would be the spectrum, low resolution spectrum for this compound. Now look at this compound and how many environments of hydrogen atoms are there. Look at all CH3. All CH3 are in the same environment. And look at this CH2, CH2, CH2. This all 4 CH2 are in the same environment. So here you get 2 environments and you will get 2 peaks. And the peaks ratio, here the hydrogen atoms ratio are, here you get 12 and 8. 12 and 8, and accordingly you will get the ratio of the peak. But just one more thing. I just change here, this is CH2 and OH. Now, can you identify how many environments of hydrogen atoms here? For this CH3 and this CH3, how many hydrogen atoms here? 9 hydrogen atoms, all 9 in the same environment. And here you get another 6 hydrogen atoms, is 2, 2, 2, and 6 hydrogen atoms would have same environment. But this part is totally different from them because this contains OAs. So this is a unique environment. This is another unique environment. These two are not same. Why these two are not same? Because this contains OH, this doesn't contain OH. So these two are again different environments. Here 2 hydrogen atoms, here 2 hydrogen atoms, and lastly OH is in another hydrogen atoms, 1 hydrogen atom. Here after you learn this, remember after you are complete to understand the environment and in different environment hydrogen numbers, then you can proceed on to high resolution spectrum. High resolution spectrum works on the same principles, that is the tiny nucleus and environment, all are okay. But this is a more sensitive device than low resolution spectrum, the advanced device. And in the spectrum, you will get peak like this. And in low resolution, you just get healthy peak. And here there is a split lines. And this also indicates that number of environment. Here you get, this is one environment, this is one environment, and this is another environment. And for this, I'm giving you a simple formula which is called n+1. What does it mean? The peaks you got in the low resolution spectrum, the peaks for ethanol, you got 3 peaks. The peaks will split into lines, okay, and the lines number split into lines. The lines number will be n plus 1. What is n? N is the number of hydrogen atoms in the adjacent carbon atoms. You got the example for ethanol. I write again ethanol, and you already got the peak in low resolution spectrum. In the high resolution spectrum, you will get peak. The peak would be like this. The one will be like a straight line. Another one will be here you get 1, 2, 3 and 4 lines, and another will be just 2 lines. Understand? So how you get this? I second n plus 1, and this one you get, look, the one line that you get for this hydrogen atom. This hydrogen atom is bonded to oxygen, and whenever you will get this hydrogen atom bonded to oxygen atom, then you will get always a straight line. This C2 gives 4 peaks. And how come? N plus 1. What is that? Look, how many hydrogen atoms do you get in its adjacent carbon atoms? 3. So here is 3. And if 3, then 1, what do you get? 4. So how many peaks do you get here? 4 peaks. And 4 peaks given by this C2. And then, look, C3. And this C3 giving peak here, 2 peaks. 2 peaks means split 2 lines. And why do you get 2 lines here? Because adjacent carbon atoms contain 2 hydrogen atoms. So n here 2. If n is 2, then n plus 1, what do you get? 3. N plus 1, 3. So that should be 3. Here would be 3. So look at this compound here, these 2 same environment, 1, 2, 3, 4, 5. So you get 5 environment in the low resolution spectrum. What you would get? 5 peaks, just 5 peaks. This is a low resolution spectrum for this compound. Look how this peak will split. This peak will split into 2. Why 2? Because look, the adjacent carbon atom is this. Adjacent carbon atom is bonded with 1 hydrogen atoms. So what is the formula? N plus 1. N is here 1 hydrogen. So this will split into 2. So I write here 2 lines. And now get how this would split. This stands for these hydrogen atoms. Look, how many hydrogen atoms do you get in the adjacent carbon atoms of this carbon? Here 3 adjacent carbon atoms. One is this, another is this, another is this. And here is 3 and 3, 6, and here is 2. So how many hydrogen atoms do you get in the adjacent carbon atoms? 8. So this line will split into how many? 8 plus 1. That would be 9. So here you should get 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then now look at this. This stands for this group C2, 2 hydrogen atoms. And look at the adjacent hydrogen atoms. Here look at, in this carbon 1 and this carbon 2. So 3 adjacent hydrogen atoms. So 3 plus 1 is 4. So you will get here 4. 1, 2, 3 and 4. You get here 4 lines. For this C2, you get this side you have carbon, this side you don't have carbon atoms. So carbon atoms contains 2 hydrogen atoms. So 2 plus 1, what do you get? 3. 1, 2 and 3. And lastly waste, and waste doesn't split, that always give a single line. So this is how you will get the splitting pattern of this compound. This is an NMR of high resolution.